Hello, good morning all. Um, Today we're going to learn about potentiometer. What is a potentiometer? Explain principle of potentiometer and its uses, and solve problem involving potentiometer. We're going to continue in next class. Okay, so uh, potentiometer is a circuit that looks like this. It contains one a big, we call as it is, you can see a one big loop over here. Okay, so current goes from positive and goes back to the negative. Okay, so it has a junction at A over here. It's not actually a junction, it's on one loop. So A to B, A to B is actually it's a wire. Okay, and then we have another source of battery. There are two over here. One's over this one, second over this one. Okay, source of second source battery, and the second source battery was connected to a galvanometer here. So G is a symbol for galvanometer. Galvanometer shows you is the function of galvanometer is to show is there any relative current that goes through the wire. Okay, and then end of the galvanometer here we have a jockey. How does a jockey looks like? This is a jockey over here. Is steel, looks like a pen, and on the end of the tip of the pen it will be sliding through the wire. So you can see the wire here on top of the ruler. So the wire you can see there over here is actually from A to B, and the jockey over here is on top of the wire. Okay, so that's the basic principle of a potentiometer. Okay, so the potentiometer is balanced when the jockey or the sliding contact is a such a position wire AB there is no current through the galvanometer. So this pen or jockey will be sliding left or right, oh sorry, left or right, okay, depending, until we have a galvanometer here shows a zero deflection. Okay, zero deflection means that there no current uh, pass through the galvanometer. So the jockey can be sliding to the left over here or to the right over here, left and right. Okay, so we have to get the galvanometer being zero, then we can use the principle of potentiometer. Okay, so when potentiometer is in balance, the unknown voltage or potential difference across being measured is equal to the voltage across AC. So Vx equals to VAC. So it means that Vx, this potential over here, Vx equals to VAC. Okay, both of them are equal. Okay, so Vx equals to VAC. So potential can be used, okay, to measure an unknown EMF of a cell, okay, such as this one. Let's say you want to find how much is the potential of this EMF. You can find it, okay, by using this potentiometer. Also, you can measure the internal resistance of a cell, okay, measure the EMF of the thermocouple, measure an unknown EMF of the cell. Okay, so in case we have here second case where a potentiometer is set up as a figure here, which is AB is a Y uniform resistance and J is a sliding jockey of the wheel. Okay, so here we have a jockey and slide. You can start from C and you can start to D. Okay, slide left and right, C and D. If you have a jockey stop at the C point of the C, we have L1. If the jockey stop at the D, we have L2. Both are in different length. Okay, so this same as the uh, primary circuit. Okay, so this is second circuit. Second circuit we have two EMF, one over here E1 and one over here E2, and we are connected to a switch. Okay, the galvanometer can go to the first switch or the second switch. Okay, so an accumulator X maintains a steady current I through the wire AB. Okay, so this X supply such a energy of a current that goes from A, goes to B, and goes back to A. So initially, a switch S is connected to the terminal 1. So it was connected to terminal 1, and the jockey moved E1 exactly, balance the potential difference from the accumulator. Accumulator reading is 0 at point C. Hence, also it means that when it was connected to the first terminal over here, we are measuring the potential divider on E1. We have found out G equals to 0 at C. If you turn left and right, you cannot get a 0, but exactly at point C, you have a 0 G. Okay. Hence, E1 equals to BAC. So E1 equals to BAC. I'm going to draw BAC over here. Okay. So this E1 equals to potential difference between E1 equals to BAC, where BAC equals to IRAC. Okay. So V equals to IR, VAC equals to I, and RAC. So resistance between A to C. Okay. Remember the current does not have any junction, so the current still flow in the one closed circuit. Okay, and RAC equals PL1 over A. Okay, remember the resistance because of the length of the wire, so rho L over A. Then E1 equals to Pi over L. Okay, this is number 1. After that, the switch S is connected to terminal number 2, and the jockey move to EMF to balance the PD from the accumulator at point D. So we say that the gamma meter was connected to E2. Now we find out that E2 is equals to at the D over here. Okay, so it equals to the VAD. Okay, E2 equals to VAD. Hence, E2 equals to VAD, where VAD equals to IRAD. Now, the length is longer, L2. And RAD, rho L2 over A. Then, E2 equals to rho I over A L2. This is second statement or second equation. Okay, by dividing equation number 1 and equation number 2, then we have here E1 over E2 equals to L1 over L2. Okay, by using the same circuit in the shown in figure 18.36, the value of unknown EMF can be determined if the E1 is replaced with a standard cell. Okay, a standard cell is one which provides a constant and accurate known EMF. Thus, EMF2 can be calculated by the equation 18.29, means like this one. Okay, you can find how much is uh, the EMF by using by using two batteries. Okay, measure internal resistance of a cell. Okay, consider a potentiometer circuit as shown in figure. So we have here one, same as before, one main circuit, primary circuit, and here we have secondary circuit. Okay, secondary circuit, can see here it was connected to by a wire. This is one wire going to A, one wire going to the G first, gamma meter, and goes to the C. Okay, goes to the C. There. Okay. So first primary, remember the primary circuit contain a battery. It contain also a wire from A to B. The secondary circuit, we have a, a battery, and the internal resistance of battery. Actually, this is inside a battery. If you have a battery, remember the battery must has at least a little bit of internal resistance. So this is inside the EMF, the battery, and we have a resistor on the bottom. Okay. So accumulator of EMF maintains a steady current I through the wire AB. Initially, the switch S is open and the jockey J move until the EMF E1 exactly balanced to the EMF from the accumulator. Gamma meter reading is 0 at point C. Hence, E1 equals to VAC. So E1 here equals to VAC. It means that this Okay, this V is equals, I put A, VA, E1 equals to this VAC on the top. Okay, hence E1 equals to VAC, where VAC equals IRAC and VRAC equals to rho L over A. Then E1 equals to rho I over L LO. First equation after the switch S is closed. Now we close the switch over here, means that the wire, the current will be moving. Okay, remember the first part, before the switch were open, there's no current that is moving in the secondary circuit. Now when we close, there will be current flow here. Okay, and current flow, and the resistance box R and jockey J move until the galvanometer reading is 0. So we find another point. Okay, point D. Oh, there will be point D over here. Okay, and shown in figure. So there will be point D at the some point to the right. Okay, L2. So there will be D over here. Okay, it means that the current now moving in the secondary circuit. Okay, so when a V equals to VAD, so V over here, this V, remember when the current flow V over here, there will be equals to IR, V equals to IR, then you have R here, you have R here, so V equals to I, R plus R, remember that. Okay, so V will be increased actually. Okay, so they will be it will not same as V before the current has flown. V equals to VAD, so VAD equals to I RAD, and RAD equals to rho L over A, then V rho I over AL, second equation. From the equation of EMF, E1 equals to V plus IR, VR, and VI, I1 equals to V over R. So R equals to E1 minus V over VR. This is third equation. Substitute, there you have R equals to L naught over L minus 1 times this R. The value of internal resistance R is determined by plotting the graph of IL against IR. So there you have here y equals mx plus c, that compare equals to y equals mx plus c. Then you have here the gradient. You can by that you can find how much is the internal resistance of the battery. Okay. So example over here, we make another basic example. Cells A and B are central 0, galvanometer G are connected to a uniform wire OS using jockey X and Y as shown in figure. Okay. So there are two jockey, one over here and one over here. The length of uniform wire OS, O to S, is 1 meter. So from this point to this point, okay, there will be 1 meter. Okay, 1 meter. And the resistance is 12 ohm. So the total resistance from O to S is 12 ohm. Okay. When OY is 75, so 0.0 O to Y is 75 centimeter. Okay. The galvanometer does not show any deflection. Okay, so we call it as a balance point. When OX equals to 50 centimeter. So here will be 50 centimeter. If Y touches the end of the S of the wire, OX equals to 62.2 centimeter when the galvanometer is balanced. The EMF of the cell B is 1 volt. Okay, so here we have 1 volt. Calculate 1A, the potential difference across O, make another color, O Y when OY equals to 75. Okay, how much is the V when OY equals 75 centimeter? B, the potential difference across OY when Y touches S. Okay, it means that Y, okay, OY touches S here, this point, and the diameter is balanced. Okay. C, the internal resistance of the cell A, how much the internal resistance R here. Okay. And D, the EMF of a cell A, how much is the EMF over here. Okay. So we go to the first one. Since wire OS is uniform, thus ROX1 equals to LOX1 over OS. Okay, ROS. Okay, this is actually very similar to a potential divider formula. Okay, so ROX1, so this is the centimeter OX divided by the whole length 1 meter and times with the 12. This is the total of the resistance from O to S. So it is only 6 ohm. So over here OX1, this is 6 ohm. Okay, from O to X. Okay, ROY1, so O, now we're going to get O to Y is 75 divided by 1 meter, 75 centimeter divided by 1 meter, 12, you have 9 ohm. So over here until here you have 9.0 ohm from O to Y. Okay, when G equals to 0, balance condition, okay, OX1 equals to EB. So when G OX1, BOX1, this BOX1 V equals to EB. Okay, this part equals to this VEB. Okay, and BOX1 equals to IR. Okay, ROX1. IROX1 equals to EB. And 1 times 6.0 equals to 1. So I1 is 0.17 ampere. So you can get the current that flows into the primary circuit. Okay, B, therefore the potential difference across OY is given by VOY R1. So if we use the same method, we can find that VOY1 is 1.53 volt VOY here. So here we have from this point to this point is 1.53 volts. Okay, so given the length, okay, so because YOS is uniform, though you use the potential divider formula, so you can find that VROX2, okay, ROX2 equals to 75 ohm, 7.5 ohm, and ROY2 is 12 ohm. So this is 12 ohm from O to Y. Okay. So B when G equals to 0 balance condition, thus VOX2 equals to EB. Okay. VOX2 equals to I square R VIR easy. Okay. So equals to, then your I2 equals to 0.13 ampere. Okay. Therefore, potential difference across OY is given by VOY. Then you have VOY equals to 1.56 volts. The EMF of cell A given are E equals to IR. In the case of question A, so you have a first equation as EA equals to 0.17, 9.0 plus R. So for case question B, you have a second equation. Okay, so 1 equals to 2, you have R equals to 0.56. The EMF for the cell A is E equals to IR. This is I, this is R plus R. Okay, so EA equals to, then you have 1.64 volts. Okay, so we're going to continue next question, next class with the Wheatstone bridge. Okay, see you again. Bye bye.